I'm going to start things over here. All right, so it is January 10th, 2022. This is totally different than what we've been doing right now. Section 4.5 is about this method we call u-Substitution. And this is finally like the chain rule for integrals, sort of. And can we please get Chromebooks away? Prima? Yes. Yep. As will it be on your test next week. Our test is 4.4.4.5. The midterm is through 5.2. So we'll include some of the things after the test. Okay. Okay. This method, this u-Substitution thing that we're about to start talking about, this is how we undo the chain rule. Integration is all about undoing things. How do we undo the power rule? How do we undo this? This is about undoing the chain rule. So I'm going to start with probably about 5 minutes of like how this thing is working, and this is maybe a little more abstract than usual, but do stick with me. The rest of today will be examples of how we actually apply this thing. So even though this may seem a little abstract in the beginning, please do stick with me on what we're about to do here. First of all, the derivative of f of g of x equals. What does it equal?
0.
Yeah, why? What did you just use? Chain rule. This is one function inside another. Take the derivative of the outside, f prime of g of x, and by the chain rule, we'll multiply by g prime of x. That's nothing new. We have a theorem that says, if I want to find the integral of f prime of g of x times g prime of x dx, I'm like asking you what has this as its derivative. Well, I know what has that as its derivative. F of g of x plus a constant. It's just the opposite of this thing. And I feel like this is obvious, but not super useful or anything right now. This is saying if you want to find the integral of the derivative of some function with another function inside of it, as long as it was also multiplied by the derivative of the function inside, well, then it's just f of g of x plus c. I think this follows directly from here, but I don't necessarily see how this is going to be helpful for us yet. Our trick for dealing with composition problems, when we have one function inside something else, is to use this method I'm about to show you called u-Substitution. And I'm going to try to do the notes in two different columns. The word stuff and then like in symbols what's going on. I'm trying to figure out the integral of f prime of g of x times g prime of x dx. I want to try to integrate that mess. The first thing that I'm going to need to do is determine which function is the inside function. Step number 1. Determine which function is the inside function. And we're going to call that u. I'm going to determine what function is the inside function. I'm going to call that thing u. This mess over here, f prime of g of x, g prime of x, well, I do see something inside something else. I'm going to call u that inside piece. I'm going to call u g of x. And there will be a little hint for trying to figure out what the inside function is that sometimes will be more useful than other times. The hint is, for something we're about to see in a moment, its derivative should show up somewhere in the problem. Does the derivative of g of x show up somewhere in the problem? Yeah, I see a g prime there. So hint, its derivative should show up. I'm going to figure out what my inside function is. I'm going to call that thing u. And, well, its derivative should show up for something we're about to deal with in a moment. Step 2. And again, do stick with me. I know this is a little abstract. We'll get to examples in a moment, but try to stick with me on this stuff. The next thing I want to do, once I have u, is calculate du, the derivative of u in differential form, in Leibniz's notation. I'm going to calculate du, which is just the derivative of u in differential form, the Leibniz notation stuff. Yeah, hold on a moment. I'm going to calculate du, the derivative of my u, and I'm going to do this in differential form. Say that one more time. Du. Du. Du is going to equal, what is the derivative of g of x? Don't overthink. G prime of x. However, since I'm doing this in differential form, I then need to multiply by the derivative of the thing inside. What's the derivative of x in Leibniz's notation? Dx. Du is g prime of x dx. Stick with me. Then, the point of all that, let me move up to the top. The point of all that is I am now going to rewrite my problem in terms of u and du. Rewrite the problem in terms of u and du. The point is, that thing inside the integral, that's just your u. And this g prime of x dx, that's just that du that we calculated. Which means I can rewrite my problem as the integral of f prime of u du, which is a much easier looking problem than that mess I gave you originally. Step 4. We're going to integrate and give the answer in terms of the original variable. So, what's the integral of f prime of u du? What's the antiderivative of f prime? F. With the u still inside there. Anything else you want to say? Plus a constant. However, The original problem didn't have u's in it. The original problem had like x's in it. So I'm going to finish this off by just replacing u with what it stood for in terms of x's. I'm going to say my final answer is f of g of x plus c. This is not a formula we're going to remember or anything like that. This is a process we're going to be using. And again, the rest of the period is just going to be looking at examples of how we can actually apply this thing. And this is one of the big ideas that will take us through like the second half of this year. This is a big deal. Can you raise your hand if you're still going? Are you still going? Okay. First example that we're going to take a look at. I want to find the integral of 2x times x squared plus 1 to the 4th dx. Which I absolutely could have handled before today. It just would have been a pain. Foil, 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 distribute, then integrate. There's a better way to do it. I'm going to try this u-Substitution method, which is what we use when there's like a composition problem with maybe some other stuff going on. Can we make sure masks are staying over noses? Thank you. Okay. U is going to be my inside function. Well, you kind of see that thing getting raised to the 4th. Couldn't it make some sense to say the inside function is x squared plus 1? Isn't that kind of inside something else? Yeah. I'm going to say u is x squared plus 1. Thank you for agreeing. And I'm then going to go and calculate du, the derivative of that thing. Well, what's the derivative of x squared? 2x dx, because we're using Leibniz's notation. And what's the derivative of plus 1? 0. So du, my derivative, is 2x dx. Well, here's the deal. Over here, that thing is my u. But the other stuff that was in that problem, that 2x and that dx, those things together are my du. Which means I could rewrite this problem as the integral of u to the 4th du. A much simpler looking problem. Do you see how I turned this into that? What questions do you have so far? Well, our next step is to go and do that so much easier integral that I know how to handle. What's the integral of u to the 4th? Well, u to the 5th over 5 plus a constant. However, I shouldn't give an answer in terms of u because there was no u in the original problem. I just kind of made up this u thing. I want to replace the u with what it stands for. I'm going to say my answer is 1/5. What was u? X squared plus 1. So I'm going to say x squared plus 1 to the 5th plus a constant at the end. I'm not going to do this right now, but if I felt like finding the derivative of this using chain rule, yeah, I'd get my original problem back. We're picking out our inside function. By the way, I made a comment on the previous page that said the inside function, its derivative should show up. Well, did the derivative of x squared plus 1 show up? Sure it did. I had a 2x over there. I then rewrote this problem. I saw that this was my u. Everything else was my du, so I could rewrite, and I could go. I have a feeling I know what you're going to ask, and if it is, I'm not going to want to answer it yet, but ask anyhow.
I was going to say, is there going to be harder ones?
Yes.
I was going to say, couldn't you just like bump up the variable one?
Yeah.
That x squared?
Hold on to that. We can do some things, we can't do other things. And yes, your question was exactly what I thought it was going to be. Let me show you a few more that are not going to be terrible yet. Let's try the integral of 3x squared times the square root of x cubed plus 1 dx. You know what? How about you see if you can figure out your u, your inside function, calculate du, and then stop. Michael. Absolutely, and this would be a real pain to multiply out. And this one, there's no other way to do it. You can't multiply things out with a square root in there. So we've got to use this new undoing the chain rule method. Hands to tell me what u is? X cubed plus 1. Okay, Kevin, what's du? Did that show up in the problem? Of course it did. That was really nice and convenient. So we can do something like this. And I think now this becomes the integral of the square root of u du. Ronak. A little louder, I can't hear you. You forgot how to do what? The derivative. We're pulling down the power, we're subtracting 1 from the power, and we're sticking a dx at the end. The power rule for derivative says move the power out front and subtract 1 from what the power was. 3x squared dx. Right? Yes? It's all coming back? Please don't scare me. Finish off the problem, please. Go do your antiderivative now. You're going to have to rewrite it, obviously. I'm going to pretend that didn't happen. Oh, no. So there is no square root in my u. I'm making u the thing inside there. So I can now rewrite my problem as the square root of u. The square root is still in the problem. It's not part of what the u was. I made u what was under the square root, so I'm going to be left with square root of u inside the integral. And now you're going to go do your antiderivative rules for that. Power rule, add 1 to the power, divide by the power. Maybe.
Is this direct or indirect?
What do you mean? Direct?
Like the integral? There's like one with the...
Oh, implicit? No. Oh, particular or... These are general solutions because there's a plus c in there because I didn't tell you enough information to find the c. This should be u to the 3 halves over 3 halves. Plus a constant, or 2/3, times x cubed plus 1 to the 3 halves, plus c. Maybe? No, these are antiderivatives. So, if we go back to that original really messy, ugly formula that I gave you, I'm talking about finding the integral of something whose derivative is also there, that g prime thing. That's kind of what the du is. It's the derivative of that inside function. Well, because this is how all integration works. Remember, we're using Leibniz's notation. That's asking what has the derivative of root u du if we're using his notation. Well, the original problem won't have a du in it or anything like that.
But even if x 3 billion x to the 100,000, divided by 4, it wouldn't affect our final answer right now, right?
No, but when you write an integral, there should be a du in the problem.
But what it is,
du is the derivative of what u was, and the only reason we're even allowed to do this in the first place is because I had that 3x squared dx in the problem. That's the only reason we can do this. One more like this, and then we're going to make them more involved. Let's take a look at the integral of the secant squared of x times the tangent of x plus 3 dx. So why do we need chain rule? Well, doesn't look like it. Looks like it's a product, so we can use the product rule for integrals. Do you know that? Oh, haven't learned a product rule. I guess we could distribute. But if we do, that's not really going to give us, that's going to give us integrate secant squared x tan x plus 3c. That's not going to give us much of anything good. So I need an inside function, which looks strange here. Why would you say tan x plus 3?
It's in parentheses.
inside this
It's in.
Remember I said u is the inside function, but also the derivative of u should show up. Does the derivative of that show up? Sure it does. That's kind of why I have that secant squared thing out front. We're going to say u. Please stop talking. Sure, it's in. I could have put that in parentheses too, though. U is the tangent of x plus 3. Its derivative is the secant squared of x dx, which again is what I have over here and all that stuff. So I can rewrite this problem as the integral of, what is this? U du. And if you don't like it, you could say it's u to the first du. Finish it off. So there are other things we could try. We could say, secant squared x, that's like secant x squared. I can make u secant x. Its derivative would then be secant x tan x. I don't have that anywhere. I want u to be something whose derivative is also showing up, and I know I've got the derivative of tan. That's why I chose it like that. And some of this is also just, you need to see a few, and then you'll kind of start seeing the pattern. I've got this over here, so I'm going to make this the u rather than making that the u. Because you just kind of need to see a few of those to get used to this. Hold on to that. I don't want to answer that yet. They've all worked out so far. Let's stick with that. You should get u squared over 2 plus c, or 1/2 times tan x plus 3 squared plus a constant. You didn't do that. Question, Maggie? I'm integrating u to the first. U squared.
I did do that. I just did everything over.
Fine, that's the same thing. Michael. It doesn't. It doesn't. Next. Okay. For this next problem, I would like you to find the u. I'd like you to find the du, and then I'd like you to figure out, but don't say yet, what the problem is. Find your u, find your du, and then figure out what the problem is going to be. Don't say it yet. U. No, forget like the fact that it's weird. Go back to like what we've been doing. What should u probably be? X squared plus 1. Fine. Du. What is du? 2x dx. Okay. Here's the deal. Does it show up? No. Here we go. If your derivative isn't exactly showing up, but your variable stuff is all there, you're just off by a factor of a constant, we can still make this work. Watch what I can do here. I've got the integral of x times x squared plus 1 squared dx. I don't want an x inside there. I really want a 2x inside there. So I'm just going to put a 2 inside there. Can I do that? Well, yes, only if you also do what? I can stick a 2 inside if at the same time I stick a 1/2 outside, because isn't this problem now the same as the original? But the point is now it's in a form where I can use this u-substitution because I have now exactly what I want for my u. Well, not for my u, for my du. I'm going to write down in words in a moment what I'm doing, but I was able to turn this problem into 1/2 times the integral of u squared du. I wasn't able to do that, though, until I multiplied inside my integral by 2, but then immediately canceled it out by multiplying outside by 1/2. Finish. Do the integral, and then just rewrite the answer in terms of x's. This is 1/2 times u to the third over 3 plus a constant. So I think like 1/6 x squared plus 1 to the third plus c. so I want to add in a little note here. Sometimes our du isn't exactly what we want. Sometimes our du that we calculate isn't exactly what we want in the problem. In fact, most of the time will be like that, where you have to do some adjusting. Please get the mask up, Ronak. If the variable part is correct, but the constant isn't, if the variable part is correct, but the constant isn't, we can multiply inside the integral by a constant and cancel it out by multiplying outside by its reciprocal. Sometimes our du isn't exactly what we want. The variable part of the du has got to be correct. So what Kevin was asking about earlier, well, can't you just like multiply by variable? You can't mess with the variable stuff, but we can mess with the constants, which does mean by the time we're done, there's still going to be plenty of integrals that we can't handle. But if things are in the form where we've got an inside function and the variable part of its derivative is showing up, if the constant isn't right, we can make that constant part work. DK. Over here, what's a constant times a half, though? Still just a constant. So we can just leave it as plus c. Okay, so I need to show you a few more of these. Let's take a look at the integral of x squared over the square root of x cubed plus 1 dx. I would like you to find u, du, and then stop. I would like you to find u and du, and then please turn around. Thank you. So I think u is going to be x cubed plus 1. I think du is going to be 3x squared dx. Is it good already? Can you make it work? Yes. What inside? 3. You know what? Maybe will green show up? Yeah, kind of. I'm trying to do different colors, but it doesn't totally work. 3 inside, what outside? 1/3. The whole point of that was because you're 3x squared and you're dx, that all becomes du. This problem is now 1/3 times the integral of 1 over the square root of u du. See if you can finish that. You have some rewriting you need to do, and then integrate. One-third times the integral of u to the negative 1/2. Remember, you can't handle 1 over root u, but you can use laws of exponents to rewrite things.
So could you take the 3x squared with u?
Say that one more time. U is 3x squared dx, because that's the derivative of x cubed plus 1. Right, I added in my 3, so now I have the 3x squared dx. I made the thing up top and the dx at the end my du. If you make u x squared, its derivative is 2x. You don't have that showing up, plus you got that square root to deal with. That isn't taken care of. This should be 1/3 times u to the 1/2 over 1/2 plus c. Well, over 1/2 is like saying times 2. I think this will be 2/3 times x cubed plus 1 to the 1/2 plus a constant. Are you seeing this adjusting thing? The multiply inside, multiply outside. Usually they're not going to be exactly perfect. You're going to have to mess with the constants a little bit. I'd like to show you 2 more. I think I only have time for 1 more. 1 more. The integral of 7 x to the 5th sine x to the 6th minus 2 dx. Find u, find du, and then stop. And while this happens, I'm going to start passing out the homework. Find your u, find your du, and then stop. What's your question? How would you do this one? It's the same thing as this one. Because the derivative, the du, wasn't showing up. I have an x squared, but I want 3x squared. It's the bracket. And same deal there. I wanted 2x, I only had x. Now there's an easier way. There's an easier way. Okay. So, u. U is what? Du. No. Okay. What's your problem? The 7. Now, is the 7 helping anything for us? No. So how about forget about u-Substitution for right now? Couldn't I just, by my constant multiplier rule, just kind of bring it out front?
Yeah.
I can make this problem 7 times the integral of x to the 5th. This is not u-Substitution work. This is just like constant multiplier stuff. I think now this is going to make it easier for me to go on. What do I really want inside there with the x to the 5th? Multiply inside by 6, outside by 1/6. We've now turned this into 7 over 6 times the integral of, let's see, that whole thing is wrapped up in my du. So sine u du. Finish it off and integrate. Thomas, question? See if you can finish this off. While you're finishing, I also have the unit review packet to pass out. I just want to kind of get them out because we're 1 day away from being done with the unit, with the test next Wednesday, I think. Okay, so we're going to get 7 over 6. Help me out. Cosine u or negative cosine u? Negative because it's an antiderivative. So my answer is negative 7 over 6 times the cosine of x to the 6th minus 2 plus a constant. Your homework. We're going to take one problem off I didn't think we'd get to anyhow. Elizabeth, when you have a moment, could you erase 17 up there? You are not doing this entire packet. You're going to do 1 through 8, all of those, and 9 through 15 odd. One last bit we'll deal with on Wednesday. We'll deal with definite integrals and a little variation on this. If you can put the chairs up, that would be helpful.